In the last two lessons, we discussed harmonic waves. In today's lesson, we will discuss a special type of harmonic waves called harmonic sound waves. Well, what are sound waves? How is sound produced? Well, sound is produced by any vibrating object. You can see sound is produced by any vibrating object. If I have my aluminum pointer hit something, you can see it produces sound. So sound is produced by vibrating object. When an object vibrates, it sets air particles into vibration, and that vibration is handed over from particle to particle so that the energy of vibration travels from one place to another. When I am talking, what is vibrating is my voice cord. My voice cord sets air particles into vibration. What type of vibration? What type of wave is sound waves? It is actually a type of longitudinal wave. Now look at this object. This is called a tuning fork. If I hit this, I set this into vibration, and listen to this. You are hearing the sound of vibration of this tuning fork. So actually, sound is a form of energy. Is that right? Sound is a form of energy transfer which needs a material medium to propagate through. If there is no air between the camera and me, you will not be able to hear me. Sound travels through a medium. Now, when I speak, I set the air particles into vibration, and that vibration eventually reaches the camera, which then records the same vibrations. Sound is propagated through solids, liquids, and gases in the form of longitudinal waves. What are longitudinal waves? In a longitudinal wave, the particles vibrate back and forth. The wave advances in the same direction. When I say the same direction, remember, it doesn't mean if the particle vibrates backward, the wave will move backward. Well, if the particle vibrates back and forth, a wave moves to the right as well as the wave moves to the left. So the particle vibration and the direction of propagation of the wave are basically the same. In a longitudinal wave, the direction of particle vibration is the same as the direction of propagation of the wave. Of course, we already said sound is produced by vibrating object. Now here I have shown something similar to the tuning fork. Now a vibrating object has an equilibrium position and two extreme positions. Now, if the vibrating object is at the left extreme, as it moves to the right, it will push the particles of the medium together, forming a region of high density. You remember, longitudinal waves have regions of high density and regions of low density. Regions of high density are called compressions, and regions of low density are called rarefactions. Well, how are these formed? As the vibrating particle or the vibrating object moves from left extreme to the right extreme, it pushes the particles forward, and that is where you have a region of compression. When the vibrating strip moves back to the left, it creates a space. That means the particles will vibrate back, and that is the region of rarefaction. So, take note of this. If a particle is vibrating forward, A particle vibrating forward is in a region of compression, and a particle vibrating backward is in a region of rarefaction. Remember, the vibration of a particle has two parts. It vibrates forward and then backward. During the forward vibration, the particle is in a region of high density. During the backward vibration, it is in a region of low density. As the vibrating object moves from extreme left to the extreme right, the particles of the medium are pushed to right, and a region of high density called compression is created. And this region of high density is propagated to the right. Now, in the same way as the vibrating object moves from right to left, the particles of the medium are pulled back, creating a region of low density called rarefaction. And these compressions and rarefactions advance through the medium, and when it reaches your eardrum, that compressions and rarefactions apply varying pressure on your eardrum, making your eardrum vibrate exactly the same way the object is vibrating. That means you hear that sound. The particles of the medium are thus set into simple harmonic vibrations. The air particles are set into simple harmonic vibrations. That means sound waves are harmonic waves. Now, when the particles vibrate in the direction of the wave, they are in a region of compression, I told you that. And when the particles vibrate in a direction opposite to the direction of propagation, they are in a region of rarefaction. Now, let me see if I can illustrate that on the diagram here. So, if a particle is in a region of compression, look at that, the particle here will be vibrating to the right. And when it is in a region of rarefaction, it will be vibrating in the opposite direction. So, a particle in a region of compression, it's vibrating to the right. A particle in a region of rarefaction is vibrating to the left. Okay. The compression and rarefaction in a longitudinal wave is actually analogous to the crest and trough of a transverse wave. Now, if you notice, it is much easier for us to draw the crest and trough of a transverse wave than to draw the compressions and rarefactions. So even where we want to draw a sound wave, we will use the transverse wave form, the crest and the trough. But remember, when you draw a crest, it means a compression. When you draw a trough, it means it is a rarefaction. There you are. So I have drawn now a transverse wave form. The crest of the transverse wave corresponds to the compression of the longitudinal wave, and the trough of the transverse wave corresponds to the rarefaction of the sound wave. Okay. The vibrations of particles at the center of a compression differ in phase by pi with those at the center of a rarefaction. You understand that, don't you? Because at the center of a compression, if the particle is moving to the right, at the center of a rarefaction, the particle is moving to the left. So their state of motion, or they are completely out of phase, or the phase difference is pi. The phase difference between a particle at the center of a compression and a particle at the center of a rarefaction is pi. Just the same way, as the phase difference between a particle on a crest and a particle on a trough is pi. The wavelength of a longitudinal wave. Can you tell me what is the wavelength of a longitudinal wave? Now, what is the fundamental definition of wavelength? The fundamental definition of wavelength is the distance between two nearest particles in the same phase of vibration. If you watch here, at the center of a compression, the particle is moving to the right. So to find a particle that is in the same phase, you've got to go to the center of the next compression. So the distance between the centers of compression or the distance between the centers of rarefaction is a wavelength. So wavelength is the distance between the center of a compression and the center of the other compression. My arrows actually haven't come very well. I should have put the arrow like this. I actually put it at the right place, but it got shifted. Now, this is a wavelength. A distance measured from the center of one compression to the center of the other compression is a wavelength. All right. I have shown you this illustration before. You have a vibrating object. You can see this red object is vibrating back and forth. And you can see as it vibrates to the right, it creates a region of high density, and that region of high density moves away. As it moves to the left, it creates a region of rarefaction, and the rarefaction also moves away. But if you look at an individual particle, now look at any of these particles. I'm pointing on one particle. Look at the way it is vibrating. It is simply vibrating back and forth. There you are. So the particles vibrates back and forth. The particles are not moving away from their positions. That is an important characteristic of wave motion. Now, when the particles vibrate to the right, they are in a region of compression, and when the particles vibrate to the left, they are in a region of rarefaction. All right, so this, you have actually seen this before, but I showed this to you one more time to reinforce the concept of longitudinal wave. Let's now talk about the speed of sound waves. How fast does sound travel in a given medium? Now, speed of sound waves in a medium depends on how fast particle vibrations are transmitted through that medium. Now, that actually depends on how fast the disturbances are transmitted through the medium, depends on how well the particles are bound together. Is that right? And therefore, the speed of sound waves in a medium largely depends on the elastic properties of the medium. How best are the particles connected to each other so that the energy from one particle can be transferred to the next particle. The elastic properties of the medium. Speed of sound waves through water depends on the bulk modulus of water. You remember we talked about it in Physics 1. While the speed of sound through steel depends on the Young's modulus of steel. So tell me, where do you think sound travels faster? In water or in steel? Well, sound travels a lot faster in steel because the particles of steel are so well connected to each other. See, the forces are so great that when one particle begins to vibrate, that energy is transmitted very fast from particle to particle. In the olden days, people waiting for a train in a train station used to go down and put their ear on the rail to see if the train is coming from very far. You know, you could hear a train through the track, if the train is 100 miles away, whereas you cannot hear that through air. You see, the speed of sound in air is only about 340 meters per second, whereas in steel it travels over 5,000 meters per second. So the speed of sound in water depends on the bulk modulus, whereas the speed of sound in steel depends on the Young's modulus. The speed of sound in air depends on two parameters: the pressure and density of air. We represent pressure by P and density by rho. And it is given by this equation, V equal to square root of gamma P divided by rho. Now, this gamma, in the second unit of this course, we will talk about this gamma. Alright, at the moment, you need to know for air, the value of gamma is 1.4. I'll give it to you as we go on. For air, gamma has the value of 1.4. So the speed of sound in air is square root of gamma P, the pressure, divided by the density. Since the value of P divided by rho, pressure divided by density, depends on the temperature, the speed of sound in air will vary with temperature. Now, an approximate relation connecting V0, V0 stands for the speed of sound at 0 degrees Celsius, and VT, V sub T, stands for the speed of sound at T degrees Celsius, can be written as V sub T equal to V0 plus 0.6 T. And this gives you a relation between speed of sound at 0 degrees Celsius, speed of sound at T degrees Celsius, and the temperature T. That is a very useful relation to remember. Alright, let's do a small example. Find the speed of sound in air at STP. STP stands for standard temperature and pressure. And that is, standard temperature is 0 degrees Celsius, which is 273 Kelvin. Pressure is 1 atmosphere. Now, do you remember from the discussion we had in Physics 1? What is 1 atmospheric pressure in Pascal? Yes? It'll be 1.01 times 10 to the 5, 10 to the power 5 Pascal. The normal atmospheric pressure is 1.013 times 10 to the power 5 Pascal. And the density of air at 0 degrees Celsius is 1.29 kilogram per meter cube. So we got the value of P, we got the value of density, and you know the value of gamma. We have V0, the velocity or the speed of sound at 0 degrees Celsius, STP, standard temperature, is square root gamma P over rho. Gamma is 1.4, P is 1.013 times 10 to the 5 Pascal, divided by density is 1.29 kilogram per meter cube, and we get that as 332 meter per second. This is the speed of sound in air at 0 degrees Celsius. Alright, in that case, can you find the speed of sound in air at 30 degrees Celsius? All you need to do is use the relationship I gave you in the previous slide. Now, what is the relation between speed of sound at 0 degrees Celsius and speed of sound at a temperature T degrees Celsius? We have V sub T equal to V0 plus 0.6 T. And we are looking for the speed of sound at 30 degrees Celsius, and V0 we calculated as 332 meters per second plus 0.6 times 30, and that will be 350 meters per second. Now, very often room temperature is considered to be 20 degrees Celsius, and the speed of sound at 20 degrees Celsius will be around 340 meters per second. So in a problem, if the speed of sound is required, and if I don't give it to you, you should always remember speed of sound at room temperature is 340 meters per second. Now, harmonic sound waves. Well, obviously, we need to represent sound waves using an equation of harmonic waves. What is the equation of a harmonic wave we developed earlier? Any idea? The equation of a harmonic wave is yxt equal to a sine kx minus omega t. Is that right? Now, in the case of sound waves, we will represent the displacement as s as a function of x and t. We will not use y. Y is for the vertical displacements. Here, we will use sxt as the displacement of a particle at any time t, and s0 the displacement amplitude. So, in place of yxt, you have sxt, and in place of a, the amplitude, we have s0. S0 stands for the displacement at its maximum. We call it S0 is the displacement amplitude. Then the harmonic wave equation for a sound wave can be written as sxt equal to S0 sine kx minus omega t. The same equation, yxt equal to a sine kx minus omega t. When you want to represent a harmonic sound wave, we represent the displacement as sxt, and S0 stands for the displacement amplitude. Now, since the displacements of the particles are caused by pressure variations, it is more appropriate that we represent the harmonic sound wave for the pressure variations rather than the displacement variations. Do you understand what I said? This equation gives you the equation of a harmonic sound wave in terms of the displacement. How does the displacement change with time? But remember, a sound wave is actually a pressure variation, high pressure, low pressure. Is that right? Compressions and rarefactions. Compressions and rarefactions. So as a wave, a sound wave passes through a medium, the pressure variations for a compression and rarefactions. So in place of the displacement, we must use pressure variations. So our equation must now be Pxt. How does the pressure change with time? So it is more appropriate to represent a sound wave by pressure variations rather than amplitude variations. But there is a little problem there. The problem is the displacement and pressure are not really in phase. At points where the displacement of the particle is zero, the pressure in the medium is maximum. You see, the displacement is zero at the equilibrium position. And it is at the equilibrium position that the pressure is maximum. So, at a point where the displacement is zero, the pressure is maximum, and vice versa. Now, this means that displacement variation S and pressure variations P are out of phase by pi by 2. So displacement and pressure are not in the same phase. There is a phase difference of pi by 2. So if you want to rewrite this equation is for the displacement. If you want to rewrite this using the pressure variations, you must take into account this phase difference. So what all change will happen there is kx minus omega t will now become kx minus omega t plus pi by 2. That will take care of the phase difference. So if Pxt is the pressure at a point at any time t, and P0 is the maximum pressure, then P0 will be the pressure amplitude. Then we can write a wave equation using pressure at any time as Pxt equal to P0 sine kx minus omega t minus pi by 2. Instead of plus p by 2, we use negative pi by 2 because pressure lags behind the displacement. It is not leading the displacement, it is lagging behind. So the pressure is actually a phase of pi by 2 behind the amplitude. Now you know that this, when you expand using trigonometric identity, sine of theta plus or minus pi by 2 will be cos of theta. So sine of kx minus omega t minus pi by 2 is cos kx minus omega t. So the equation for the harmonic sound waves in terms of the pressure variations is Pxt equal to P0 cos kx minus omega t, where P0 is the pressure amplitude. And now you can see the same situation we have seen before. Kx minus omega t is the same as k times x minus vt. You understand that? Where k is the wave number and v is the speed of the wave. Now in the equation p equal to p0 cos kx minus omega t, omega is the angular frequency that is equal to 2 pi f. And you know that these two equations are the same. We have dealt with this several times before. The pressure amplitude P0 is given in terms of the displacement amplitude S0. Remember, we expressed this equation using the pressure. We adapted the equation from displacement. And so you must be familiar with a relation connecting pressure amplitude P0 and the displacement amplitude S0. It's an important relation. It is P0 equal to rho omega V S0. Rho is the density of the medium. Omega is the angular frequency, that is 2 pi f. V is the speed of the wave. S0 is the displacement amplitude. P0 is the pressure amplitude. So a relation between pressure amplitude and displacement amplitude. Okay, let's do an example. A sound wave in air produces a pressure variation given by Pxt equal to 0.75 cos pi by 2 times x minus 340 t. Now, can you tell me what form is this equation? Well, this is of the form Pxt equal to P0 cos k times x minus vt form. Is that right? So your k is pi by 2. V is 340, that's the speed of the wave. So, where P is in pascals, the pressure is measured in pascals. X is in meters. T is in second. find the pressure amplitude of the sound wave. Well, there's nothing there to find. It is there. This is the pressure amplitude of the sound wave. The wavelength lambda is contained in K. Remember K. K is 2 pi divided by lambda. And you know K equal to pi by 2. The speed of the wave, again there is nothing to find the speed. The speed is this, x minus vt. So that is your speed. And the frequency. Well, if you know your speed and wavelength, then you can find the frequency. So these problems are very simple for you. Let's put these things together. Compare the given wave function with the general form pxt equal to p0 cos k times x minus vt. This is the general form of this. So you got p0 is 0.75, k is pi by 2, v is 340. Pressure amplitude is 0.75 Pascal. The value of k in this expression is pi by 2. But k equal to 2 pi divided by lambda. So we say 2 pi divided by lambda equal to pi by 2. Can you solve for lambda from here? Well, I can tell you from one look, pi and pi cancels. Lambda equal to 4 meter. So you obtain the wavelength. Alright? What is the speed of the wave? The speed of the wave is 340 meter per second. Well, and finally the frequency. Frequency F equal to V over lambda. We know V is 340 meter per second. Lambda is 4 meter. Therefore, the frequency is 85 Hertz. Alright, so that means once you know the harmonic wave equation, you have practically all the information about that wave in that equation. Alright, let's do another problem. Example 4. What is the displacement of a sound wave having a frequency of 100 Hertz and a pressure amplitude of 10 to the power of negative 4 atmosphere? Well, you know there is a relationship between pressure amplitude and displacement amplitude. And part B, the displacement amplitude of a sound wave of frequency 300 Hertz is 10 to the power of negative 7 meter. What is its pressure amplitude? Alright, so both these are using the relation between pressure amplitude and displacement amplitude. Well, I don't think you remember that equation I gave you. Let's pick the data. Pressure amplitude in part A. Pressure amplitude is 10 to the negative 4 atmosphere, which when converted to Pascal, remember, atmosphere can be converted to Pascal by multiplying by this. This is 1 atmosphere in Pascal. So we know we have P0, we have the frequency 100 Hertz, we have the speed as 340 meter per second, and this is the relation between pressure amplitude and displacement amplitude. We need to find the displacement amplitude, so we need to solve for S0. S0 is P0 divided by rho omega V, and we know all those values, don't we? Now P0 we know, this is P0. Rho, the density of air, you remember I gave it to you, 1.29 kilogram per meter cube. Omega is 2 pi F, where F is given to us. V, the speed is 340 meter per second. So put all those values and calculate S0, it gives me 3.67 times 10 to the negative 5 meter. And that is the displacement amplitude of this wave. Okay, let's do now B. In B, you are given the displacement amplitude. You are given the displacement amplitude. You need to find the pressure amplitude. So we go directly to the equation. Pressure amplitude is rho omega V S0. We know all these values. Rho is 1.29 kilogram per meter cube. Omega is 2 pi times the frequency. Frequency is 100 hertz. So that will be 2 pi times the frequency. Isn't the frequency 100? Well, V is 340 and S0 is 10 to the power of negative 7. So I think this 300 must read 100. Is that right? Yes. So we must change that for you. That will be the pressure amplitude equal to 8.27 times 10 to the negative 7 Pascal. Okay? Let's now talk about another concept of sound. Intensity and intensity level of sound waves. What is the meaning of intensity? How intense is the sound? Now remember, sound wave is generated by a vibrating object. That means a vibrating object has a certain amount of energy, right? So this object gives out a certain amount of energy. Intensity is measured in terms of the amount of energy that passed through a certain region. Suppose I want to find the intensity of this sound where I am standing. Now, the intensity of the sound where I am standing is a measure of the energy from here that passed through a point where I am standing. Okay, we have to make it a little more concrete, the definition of intensity of sound waves. And then we will distinguish between intensity and intensity level. Alright, so pay attention to this. A vibrating object sends out energy in all directions. The amount of energy emitted by the vibrator in 1 second is called the power emitted by the source of sound. Now, most of you know that you talk about the power of your loudspeaker, don't you? What does it mean when you say your loudspeaker has a power of 300 watt? A watt is joules per second, energy given out per second. In other words, the energy given out by that loudspeaker every second is 300 joules. That loudspeaker has a power of 300 watts. So the amount of energy emitted by the vibrator in 1 second is called the power emitted by that vibrator. The intensity of the sound at a point, a distance r from the source, is a measure of the power crossing at right angles to unit area containing that point. Now what does that mean? Suppose I take a unit area. What is a unit area? A unit area is an area of 1 meter square. Suppose this is the paper I crumbled some time ago. Suppose this is a unit area and I have an object vibrating in front of me. Now I want to find the intensity of that sound at a point here. All I need to do is take a unit area containing that point and measure the total energy crossing at right angles to that unit area. You see, that is a measure of the intensity. So what is the intensity again? The intensity of a sound at a point is a measure of the energy, the amount of energy crossing at right angles to a unit area that contains that point. And we will represent intensity by I, and it is measured in watt per meter square. In other words, intensity at a point is a measure of the power that is crossing at right angles to a unit area that contains the point. Suppose I want to find the intensity of a particular sound, that is, the source is somewhere there. Now, to find the intensity, what I do is I keep a unit area where I'm standing and measure the power crossing this unit area, and that will give me a measure of the intensity of that sound. The intensity level of a sound determines how loud the sound is. So, look at this. They are not the same thing. The intensity of a sound is the power crossing unit area containing that point. Whereas intensity level is actually the loudness of the sound, how loud the sound is. Now, how loud the sound is depends on the amplitude of vibration of the particles. Now, the intensity level represented by beta is a logarithmic function of the intensity and is given by, now, the intensity level, which is the loudness, is actually determined by the intensity, and there is a relation connecting the two. The intensity level beta is related to the intensity of the sound I by a logarithmic function. Well, you know what a logarithmic function is. Now, here is that function. Beta equal to 10 log I over I0, where I is the intensity of the sound whose loudness we want to find, whose loudness is beta. And I0 is what is called the threshold intensity. So here I is the intensity of the sound of which we want to measure the intensity level beta, and I0 is the threshold intensity. In other words, threshold intensity is the intensity of a sound that you can barely hear. For example, can you hear when you breathe? I'm breathing. I can barely hear. But there is a sound, because when you breathe, your nostrils are vibrating, and that vibration produces a sound. But you can barely hear it. And that sound, or the intensity of such a sound, is I0, called the threshold of intensity. And the threshold of intensity has a value for human ear. It is 10 to the power of negative 12 watt per square meter. So wherever you want the value of I0, always use this value, 10 to the power of negative 12 watt per square meter, and that is the threshold of intensity. Intensity level beta is measured in a unit called decibel. So beta is measured in a unit called decibel. Look at the way we write the decibel in short form. It will be small d, big B, decibel. Now notice that the difference between intensity I measured in watt per meter square and intensity level beta measured in decibels. They are not the same, although the intensity level beta is determined by the intensity I. Beta equal to 10 log I divided by I0. That's an important equation that connects the intensity level and the intensity of a sound. Now here I have a table. I don't know whether you can see all of it on your screen. Normal breathing is intensity level. The intensity level is 0 decibel. See, normal, well, barely audible. The threshold of intensity is 0 decibel. You see, that is not normal breathing. Normal breathing you can hear. Now you tell me that is not normal, that's abnormal. But normal breathing you can hear. It is 10 decibel. It's barely audible. What is the intensity level of threshold? Is 0. Rustling of leaves is about 20 decibels. Now look at that. Busy traffic, 70 decibels. Heavy truck rolling by Niagara Falls is about 80 decibels or 90 decibels. Now, constructed noise is about 100 decibels. So you can see what will be the decibel value of my voice. You see, I normally speak very loud, and I know some of you must have actually had difficulty getting the volume adjusted, because when you open this video sometimes it blares out because I speak very loud. You got to control your volume so that the decibel value is more comfortable for you. Is that right? Okay, so I just gave you these for guideline only. Let's do another example. What is the intensity level of a sound wave of intensity I equal to 10 to the power of -10 watt per meter square? I have given you the value of intensity. I want you to find the value of beta, the intensity level. Alright, do you remember that equation I gave you? Beta equal to 10 log I over I0. You got the value of I, and you know the value of I0, don't you? I gave it to you. What is the value of I0? It is 10 to the power of -12 watt per meter square. So use the values of I and I0. That will be 10 log, I is 10 to the -10, I0 is 10 to the -12. Now what is 10 to the -10 divided by 10 to the power of -12? That will be 10 to the power of 2. So this will be 10 log 10 to the power of 2. Alright, is there anybody who has trouble with this? What is log 10 to the power of 2? Log of 10 to the power of 2 is 2. In other words, the decibel value is 20 decibels. And in my table, 20 decibel correspond to the rustling of leaves. When a breeze comes, the leaves rustles, about 20 decibels. Alright, let's do another one. The sound of a dog's bark is 50 decibel. What is the intensity of the bark? So, this time I gave you the decibel value. You need to find I, the intensity value. And the next part, the intensity of a rock concert is 10,000 times that of dog's bark. What is the intensity level of the rock concert? Alright, let's start with the first part. What are the things we know? You are given the intensity level, beta equal to 50 decibel. You need to find the intensity of that sound. Alright, I0 we know is 10 to the power of -12 watt per square meter. And we go out to our old equation, beta equal to 10 log I over I0. You know beta, you know I0, we need to solve for I. Well, if you know how to solve a logarithmic equation, which you do in your college algebra, okay, let's do it. 50 equal to 10 log I over 10 to the power of negative 12. Now, what I'm doing here is I kept the 10 outside and used the properties of logarithm. That will be log of I minus log of 10 to the negative 12. You understand that? Log of A over B is log A minus log B. Alright, can you tell me what is this log of 10 to the power of negative 12? Log of 10 to the power of negative 12 is negative 12. There you are. So that will be 10 times log I minus negative 12 is plus 12. So you got 50 equal to 10 times log I plus 12. And that will be 10 log I, distribute that 10. 10 log I plus 120. And what is this quantity equal to? 50. Alright. Next, take this 120 to the left side. Get 50 minus 120 is negative 70 equal to 10 log I. And therefore, what is log I? Divide both sides by 10. Log I equal to negative 7. Okay. If log I equal to negative 7, remember, when you write log, the base of this is 10. If the base is E, it will be ln. So log I equal to negative 7 means I equal to 10 raised to the power of negative 7. You should know that. So if log I equal to negative 7, then I equal to 10 to the power of negative 7. That means the intensity of dog's bark is 10 to the power of negative 7 watt per square meter. And now, if this is the intensity of the barking of the dog, what is the intensity of the rock concert? It is 10,000 times the intensity of the dog's bark. So the intensity of the rock concert is 10,000 times 10 to the power of negative 7. What is that equal to? That will be 10 to the power of negative 3 watt per meter square. And now you need to convert to this to decibel value, or find the intensity level of this intensity value. Again, I remind you, don't confuse between intensity and intensity level. Here I equal to 10 to the negative 3 watt per meter square. We need to find the corresponding intensity level. Alright, beta equal to 10 log I over I0. I here is 10 to the negative 3. I0 is 10 to the power of negative 12. Tell me, what is 10 to the power of negative 3 times 10 to the negative 12? Alright, that is 10 to the power of 9. So this will be 10 log 10 to the power of 9. What is log 10 to the power of 9? Log 10 to the power of 9 is 9. So this is equal to 90. The intensity level of the rock concert is 90 decibels. Okay, so I hope you have a fair understanding of the relation between intensity level. If I give you one, you should be able to calculate the other. Now, I'm going to continue this lesson as a second part. So I'm going to stop this one here. From pitch of a sound, I'm going to call it 1.4B. Alright? Okay.